All right, so I'm actually recording an extra video for Recitation 2 because we have quite a bit of problems left from last session. So to help you better prepare, the best strategy to go over the problem in this recitation is try to solve it yourself first. And if you have issue with it, then watch the video and come to the office hours. Okay, let's get started. So we start with a proof where in this particular case, we want you to prove with contrapositive statement. Again, the best way, if you're watching this video, you could pause the video right now and then try to solve it yourself and then compare your solution with my solution. But I'm just going to go ahead and talk about how I would think about this problem. All right, so the idea is that for all integer n, if n squared is even, we want to prove n is even. A way to prove it is to say if we have an implication from p to q, we know that it's logically equivalent to its contrapositive statement, which is not q implies not p. So if we're going to look at this statement, the first thing to do is to look at what is the original statement. The statement P is n squared is even. The statement Q is n is even. Then what is my not Q implies not P? This is, so if I want to write out the contrapositive statement that I want to prove is not Q, which means if n is odd, we want to prove that n squared is odd. Okay, so this is really my contrapositive statement I want to prove. So the hypothesis is n is odd, and the conclusion is n squared is odd. Okay, so there's a few steps. Number one, by definition of odd integer, n is odd. That means n is equal to 2k plus 1 for some integer k. Okay, this is by definition of odd. Step number two is now because n is equal to 2k plus 1, we can use the substitution. So by substitution, we are looking at n squared. We want to prove n squared is odd, so we want to express n squared in this new form. So n squared, substitute n to be 2k plus 1, that is 2k plus 1 squared, and that is equal to 4k squared plus 4k plus 1. And this is me using the rule of a plus b squared is equal to a squared plus b squared plus 2ab. Okay. The third step is now we have expressed n squared as 4k squared plus 4k plus 1. I need to prove it's odd. So remember, I need to, again, use the definition of being odd, and I need to do some algebra. So specifically, I'm going to do factoring. So I would factor out 2 in the expression, then n squared is equal to 4k squared plus 4k plus 1 is equal to factor out 2. 2 times 2k squared plus 2k plus 1. Okay. The next step, I have this term here. This is additional detail. I need to prove 2k squared plus 2k is actually integer. Then n squared is 2 times some integer plus 1. So in order to do that, we want to use a closure. So we want to use closure of integer under addition and multiplication. Okay, so what that means if I let a new variable m equal to 2k squared plus 2k for then by closure m is integer. Okay, then n squared is equal to 2 times 2k squared from 2k plus 1 is equal to 2m plus 1 for some m that's integer. then last bit is again by definition of odd integer. N squared is equal to 2 times some integer plus 1. Therefore, for some m integer, therefore n squared is odd. Okay, so that is the end of the proof. Okay, the most important steps in this proof is that you first need to understand what is the logic equivalence between implication and its contrapositive statement. And then you're using the definition of something being odd. You're using substitution, factorization, and then the closure property of the integer, or of integer under addition and multiplication. Okay. Integer is closed under addition, multiplication, and subtraction, but not closed under division. Okay. That is, if you take two integers divided from one to another, say a divided by b, it's not guaranteed to be integer. Okay, let's look at the next one. Next one is a little bit tricky. That's why I put 10 minutes. Again, it would be a good time to pause the video and try to solve it by yourself and then resume it to see my solution. Okay, so prove that if n is not divisible by 3, then n squared plus 2 is divisible by 3. Okay, so there's a few interesting part of this problem where you want to first process. What is the property of something being not divisible as 3, and what is the property of something being divisible by 3? When you see such a problem, one of the first instincts is to think about what is the property associated with the mod operation, which is taking the remainder. So what is, sometimes you use n, take the remainder, or you do n mod 3. And in this particular problem, I'm going to use this notation, which is taking the remainder of an integer when it's mod 3. So if something is divisible by 3, for example, if 3 divide a number n, then that means n mod 3 is equal to 0. That means there's no remainder. If 3 does not divide a number n, then it means n mod 3 is not equal to 0. But what are the possibilities? It means either it mod 3 is equal to 1, or n mod 3 is equal to 2. Okay? What does that mean? One is to say if 3 does not, if n is not divisible by 3, then when it's mod 3, its remainder is either 1 or 2. Okay? If I push it further, if its remainder is 1, then this number can be expressed as 3 times some integer p plus 1, or n is some integer q plus 2, depends on what, for some p, q that is integer. Okay, so everything I put in green is basically my sort process. So now let's write it more precisely. What are the cases, right? If I'm looking at a hypothesis, n is not divisible by 3, that means it either has a remainder of 1 or remainder of 2 when it's mod 3. So I have two cases. So case number 1, n mod 3 equal to 1, meaning that n is equal to 3 times p plus 1 for some integer p. Okay, and of course the second case is n mod 3 equal to 2, that is n is equal to 3 q plus 1 for some integer q. Okay, and now what's the next steps? For the first case, we have some sub-steps. Okay, so first step I already expressed, at the beginning I already expressed n is equal to 3 plus 1. Then now I want to do by substitution. I'm going to use sub as what I mean by substitution. N squared plus 2 is equal to 3p plus 1 squared plus 2. And now I'm going to use a bunch of algebra to simplify this. This is equal to 9p squared plus 6p plus 1 plus 2, which is equal to 9p squared plus 6p plus 3. Okay? And then now factor out 3 because we are going to look at whether this number is divisible by 3, then n squared plus 2 is equal to 3 times 3p squared plus 2p plus 1. Okay? And now this is in the form of 3 times some number. If I prove this complicated number that is highlighted in yellow to be integer, then we know that n squared plus 2 is expressed as 3 times some integer, which means that it is divisible by 3. So then what we do is by closure of integer under multiplication and addition, I will let's say k equal to 3p squared plus 2p plus 1. K is integer. Okay. Then my n squared plus 2 is equal to 3 times k, for k is integer. Therefore, it is divisible by 3, so I can just write 3 divide n squared plus 2. This is just the first case. Now we are going to do similar things for the second case, because n, again, by substitution, n squared plus 2 is equal to 3q plus, sorry, this is plus 2, squared plus 2, which is equal to 9q squared plus 12q plus 4 plus 2, which equal to 9q squared plus 12q plus 6. And I'm going to factor out 3. This is equal to 3 times 3q squared plus 4q plus 2. Again, by closure property, that let's say I'm using the variable m is equal to 3q squared plus 4q plus 2 is integer. Therefore, n squared plus 2 is 3 times integer, is divisible by 3. Okay, so that's the end of the proof. Okay, so what is the key idea from this? Again, you want to understand what is the definition of some number divisible by 3 or not divisible by 3, which is looking at the property of it with respect to taking the remainder or n mod 3. And based on that, the highlight of this proof is that you look at if I can express those two integers as either 3, under two cases, either 3p plus 1, so it has a remainder of 1, or has a remainder of 2. And then you use algebra, substitution, factorization, and closure property of the integer to arrive at your final proof. All right? Okay, so let's look at the next one. So we call it indirect proof because we want to, again, prove, for example, by the contrapositive statement. Okay, so the original proposition is to say any real number x, if 2x is irrational, then x is irrational. So if I'm using q prime to represent irrational number, then you said, if 2x is in q prime, then x is in q prime. So sometimes proving something to be irrational is actually quite difficult. So the question is, can we prove something slightly different? So in this case, right, irrational means not rational. So if we take the contrapositive statement of this, so if this is p statement to q, and if I look at not q implies not p, which is a contrapositive statement, and then let's say q represent the set of rational number, then it means I want to prove if x is not in Q prime implies 2x is not in Q prime, which is equivalent to say I want to prove if x is in Q implies 2x is in Q. What does this mean? If x is a rational number, we want to prove that 2x is a rational number. This turns out to be much simpler. Okay, so what we want to do is to prove the contrapositive statement. Okay, so here we have a little bit more space. Again, we're going to look at a few steps. The first step is, we're going to prove if x is in Q, then 2x is in Q. If I look at this problem, one of those highlight is to understand what is the definition of something in Q. So what is the definition of some number to be a rational number? So the first step is to translate the hypothesis into something I can work with, into some sort of algebra. So the first step is by definition of rational number. If x is a rational number, then there exist two integers, a and b, such that x is a divided by b. This is a definition of something be rational. It can be expressed as a division of two integers. Now, the second step is, of course, substitution, right? So I want to use substitution, look at the expression in my conclusion, which is 2x. So I want to, by substitution, 2x is 2 times a divided by b. Okay. And now the third one is I'm going to rearrange a little bit. And in this particular case, I'm using what we call by property of association. What did that mean? That means I can kind of rearrange things, expression 2x, I can write it as 2a divided by b. I can remove the parentheses and move 2 on the top. All right. So now the last step is I want to express that 2a, in fact, is also an integer. So 2x can be expressed by the division of two integer. So again, I want to by closure of integer under, in this case, multiplication. Because a is an integer, then 2a is integer since 2 is integer. Then 2x is equal to, if I let k is equal to 2a, a is integer, so k is integer. Just rewrite this. Okay, 2x is equal to k over b for k that is integer. Then, of course, the last step is by definition of rational number. 2x is a rational number because it can be expressed as the division of integer k and b. All right. So what is again, if we revisit, what is the key idea of this proof? Is really surrounding understanding what is the definition of a number to be a rational number, and then decided that, if it's a rational number, it can be expressed by the division of two integer, and then you use a bunch of substitution, and then and the closure of integer under multiplication. Okay. All right. Let's look at the next problem. So, so in this case, the proposition is to say for integer that is bigger than 4, if it is a perfect square, then n minus 1 is not prime. Okay. If we're looking at this, there is a few questions you can ask yourself. And specifically, if we're using the technique we used in the previous proofs, we need to understand what is the definition of something being a prime. Okay. So if something is prime, the only factor it has is 1 and it itself. That is the definition of a prime. But then in more detail is, how can we take advantage of the hypothesis? What is a hypothesis? The hypothesis is n is a perfect square. So if I'm thinking about it, n is a perfect square, that means maybe n can be expressed as the square of some integer, right? That is a definition of something being a perfect square. How can we prove a number is not a prime? That means I can factor out, for example, if a number is not prime, it can be expressed by two integers multiplied together such that each of the integer is not equal to 1, and they are also not equal to themselves, to n itself. Okay, this is sort of roughly the idea. How do we prove a number is not a prime? That, you know, it can be factored out into something that is not 1 or itself. Yeah, so in another way is we want to make sure both factors is bigger than 1, but also you want to make sure that they are really not equal to the number itself. Okay. So those are just some thought process that go through, but the idea is how do we actually prove it? Okay, so this is the last problem for recitation 2, extra material. So in this case, again, you know, we know that we want to take advantage of hypothesis. So we want to make make use of hypothesis, and we also want to make use of the property of something being a prime or not a prime. So of course, the first step is to say, well, by definition, by the hypothesis, n is a perfect square. What does that mean? That means n is m squared for m being integer. But because, you know, because n is bigger than 4, you know, I want to emphasize actually m is sort of bigger than 2. Okay, so this probably we might be useful later. So let's put it here. Now, the conclusion I work with n minus 1, so I want to use substitution. By substitution, n minus 1 is equal to m squared minus 1. Okay. And now, in order to prove if n minus 1 is not a prime, I need to start some sort of factoring. So I want to sort of factoring n minus 1. What I get is n minus 1 is m plus 1 times n minus 1. This is using the property that a squared minus b squared is equal to a plus b times a minus b. This is, again, a basic algebra rule that we're using here. So now if I factoring this n minus 1, it's be expressed as a multiplication of two integers, right? So first of all, we know that by closure properties, so by closure of integer under sort of addition, okay? Under addition and subtraction, we know that both m plus 1 is integer and m minus 1 is integer. However, that is not enough to show that, you know, n minus 1 is not a prime, because you need to show that m plus 1 and n minus 1 are not equal to 1 or n minus 1. Okay. So the next step is, since, again, this is where this property is going to use, is that we know n is bigger than 4, right? So since n is equal to m squared is bigger than 4, then m is bigger than 2. So then if I let a to be m plus 1 and b is equal to m minus 1, then we have a, which is m plus 1, is what? Is going to be bigger. A is equal to m plus 1 is going to be bigger than 2 plus 1, which is equal to bigger than 3. And b is equal to m minus 1 is bigger than 2 minus 1, which is equal to 1. So what does this mean? So that means the last step, since both a and b is bigger than 1, and because a and b is m, and also we want to show that the last bit is both A and B is not equal to n minus 1. Okay, so how do we show that? This is sort of fairly obvious because A is equal to n plus 1. And I'm going to use greens to convince you, is if A is equal to n plus 1, and if A is indeed equal to n minus 1, then we are going to have a contradiction. Okay, so here there is a contradiction that you should convince yourself that's indeed the case. And then, if I were convincing myself n is actually quite large and A is just a factor of it, but you really want to show this by a contradiction. So this is something, if you are confused, come to the office hour. Okay, so if in order to show that n minus 1 is not a prime, which we have showed that it's a multiplication of two integers, and then those two integers are both not equal to 1 and not equal to the integer itself, then by definition, so n minus 1 has a factor other than 1 and itself, by definition of prime number, n plus 1 is not a prime. Okay. So that's it for the extra material for recitation 2. I would highly encourage you to go over all the lectures surrounding the proof, since our quiz number 2 is coming up very soon. All right. Have a good day. Thank you.